No,
sorry, we had some technical difficulties to start with. Once this video finishes, we'll be able to continue with the live chat. Tonight, we're talking about the quantum edge AI with a roundtable of industry luminaries. We've got Jonte, Hance, Chancellor Koorosh, Aslansefat, and Oleksandr Kyriienko. Apologies if I've mispronounced any of those, who will be able to introduce themselves shortly. This video has a lot of black space. We had this problem last week. If you give it a couple of seconds, it will finish. If you're dialing in from a different part of the world, please say where you are. And if you have any questions as we're going along, please add them to the chat and we'll ask them to our panel live. And we're almost there. Is anyone else there? Is any of my panel on the call? Right, we're definitely streaming live now. Really huge apologies for that, everybody. It's usually not so fraught and hectic. Great you can join us. Could we do a little roundtable? Everyone introduce themselves. I'll go first. I'm John. So I'm mostly a software engineer, so I do some IoT and some AI stuff. I tend to ask all the technical questions. Paul, who's usually hosting, he's more sort of the charismatic face of the AIoT Hub, and I ask all the difficult questions. Tonight, I'm really glad to be here because this is a subject I know absolutely nothing about. So I'm expecting to ask lots of stupid questions, and I hope you're prepared for that. But I'm probably not the only person who's on the call who will be able to, that will benefit. So I'm hoping other people out there who are listening will be able to benefit from that. So Oleksandr, do you want to go next?
Yeah, sure, I can. So I'm Oleksandr Kyriienko. It's a full name. The short name is Sasha. I'm a professor at the University of Sheffield, and I do research in quantum machine learning. So on the theory side, we develop new algorithms, how we can train quantum devices to solve problems in machine learning, do data processing, but also come up with some generally new protocols for generating new data.
Okay, fabulous. Koorosh, do you want to go next?
Yeah. Hello, everyone. My name is Koorosh Aslansefat. I am an assistant professor at the University of Hull. I do research on AI safety and explainability. And I also recently shifted my focus on the trustworthiness of quantum computing or quantum machine learnings. So how we can make them safer or more explainable and so on. So I'm happy to be in this panel.
Great, thank you, Koorosh. Jonte, do you want to go next?
Hi, I'm Jonte. I'm current head of the Advanced Model-Based Engineering and Reasoning group here in the School of Computing, which is where quantum currently sits, although hoping to kind of spin out more specifically into a quantum group. I'm also an EPSRC Quantum Technologies Career Acceleration Fellow, which is a fun title, and I'm a lecturer here at the moment in Applied Quantum Foundations. So again, my background has kind of been coming from looking at all the weird fun bits of quantum to try and then see what we can do. And again, coming from working with a mixture of experimentalists and theorists and even some philosophers to try and just sort of see really, to understand quantum mechanics through that kind of pragmatic understanding of how can we get quantum advantages.
Right, great. Thank you for that. If we could just go back to basics for a second, can someone describe the state of quantum computing at the edge as it stands?
I mean, I'd say maybe describing it at the edge is a little bit difficult because just thinking about where edge computing is, I feel like quantum computing maybe, and again, maybe the other panelists will correct me a little bit here, I wouldn't say it's necessarily there yet. We're, again, in the process of developing some really cool kind of cloud-based quantum computing at the moment. I mean, the National Quantum Computing Center or IBM or various companies, but where it's very much a case of a quantum computer is a very big, expensive thing which is held by a company which you can access, or potentially if you're really well funded, held by your research group and you can access, rather than it being maybe edge in that same way that Edge AI is kind of coming through, where it's really embedded in sort of hardware that you have on you. Again, thinking like phones and things like that. In the near future, or maybe not near future, it would be interesting to see where we could go when it comes to quantum computing or quantum machine learning for edge applications.
Yeah, maybe I can follow up on Jonte's comment. That's exactly what's happening now. We're trying to understand how to build these machines in principle, which is a very challenging feat. So typically you will need cryogenics setup. So for some hardware, you need the actual dilution refrigerator, which is expensive and large. There are hardware modalities that can operate at room temperature, and potentially that will appear as edge quantum computer, but we are not there yet. So it's very rudimentary, open, and we should discuss how to make it happen in the future.
Okay, so do we see this as something that the cloud providers are going to sort of mop up? So if we want to have quantum computing for whatever the use cases are, we'll go on to that. They're going to have some resource that we can just buy time on.
I would say, at least in principle for the moment. I mean, part of the issue, again, as Sasha kind of alluded to, is quantum systems are naturally quite difficult to keep as quantum while you're accessing them. Again, if there's heat, if there's noise, if there's any sort of interaction, that tends to completely overwhelm that kind of quantum behavior. Again, it's a process, we call decoherence, effectively, where the quantum system connecting to its environment means that you see less of that actual quantum behavior. So, I mean, unless we want to have, dilution fridges running at 4 Kelvin in our phones and things like that, at the moment, we're maybe a little bit limited. I mean, there's some really great work going on making things that can be accessed room temperature. But I know, from an experimental perspective, my background is kind of in photonics. So I came up through Bristol's Ket Labs, where again, I remember the massive great dilution fridges that you needed for detectors, even if you were doing the computation at room temperature on these little chips and things, actually then detecting the photons at the very end without having large amounts of thermal noise is quite difficult. So I think certainly for edge applications, it would probably be having to use a, classical network, a classical kind of internet connection and things, and just directly feeding through. I mean, I think there are possibly some applications that are non-computing based that are still quantum, where there could be edge or edge-related things. I mean, quantum key distribution, for instance, being an example where I know people have built it into boxes about the same size as phones, and you kind of point it at a little device to get a...
Sorry, I missed that. Could you say that again slower for me?
Sorry, sure. So for quantum, for cryptography effects.
Cryptography, right, yeah.
Yeah, cryptography is maybe not the right word because it's not cryptographic in that same way. It's not, laws of mathematics and very hard mathematical problems. It's, the laws of physics. But being able to use quantum devices for security is maybe closer to the edge and actually devices that we can have on a person and things. Again, I'd be curious to see, Sasha, Koorosh, your kind of thoughts around this.
Yeah, so one of the issues that we have for quantum computers, or one of the concerns that we have, is that they are very capable of kind of deciphering the kind of, let's say, stored passwords and even kind of, let's say, large ones. So because of that, a lot of countries decided to do a post-quantum encryption. And nowadays, the kind of, let's say, the storage that we have for passwords and so on is post-quantum ones. But one thing that we could consider is that the quantum itself, it could be enabling us to have more secure systems or more kind of, let's say, reliable systems. Because when it comes to having optimization or finding the optimal solution, quantum computers are much more capable of finding the best solution for us. So that's one of the advantages that we have to use these solutions for finding the best kind of, let's say, outcome or kind of reliable outcome out there.
That's great. And have you noticed Nick is now in the room? Nick, if you, sorry to interrupt, but if you could introduce yourself.
Yeah, so I'm Nick Chancellor. I specialize in sort of near-term quantum algorithms and a bit of quantum-inspired. Actually, a lot of work toward things like optimization, where you are going to be using a specialized processor. So actually, the timing was really good when I ended up managing to come in, because yeah, I think that's right, and I think one thing to be aware of when thinking about, at least near term, about the impact that quantum computing is going to have on the edge is not just the quantum devices, which are coming, but they're very hard to build and it's going to take a while, but also quantum inspired algorithms, quantum inspired devices, things that aren't really fully quantum computers, but are inspired, inspired by us thinking about problems in entirely different ways. And if you're thinking about building a device that, doesn't have to be completely resistant to decoherence, but is solving a problem in, an approach that looks like quantum, that you can immediately put into an edge device. And, things like, traditionally, we tend to think of optimization problems as linear problems with constraints. Quantum mechanically, it's much better to frame them in a quadratic way. We're already, people have seen this and have started building classical devices that say, well, what if we build devices that work the way the quantum devices will work? And, that we're going to be seeing returns before we get real devices just by changing the way computer scientists think about this. Sorry, Jonte, I'll let you jump in with whatever you were going to say.
Yeah, I think I was maybe going to possibly add a note of caution to what Koorosh said. In terms of applications for quantum algorithms, I think we need to be very careful about overpromising, because there are only certain very limited cases where we know that there is an advantage from using a quantum algorithm over a classical one. And again, if you rule out these kind of variational or energy minimization ones that Nick's talking about, where we can potentially map it to classical quantum inspired ones, and if we rule out quantum simulation, I feel, we've only got a very limited gamut of useful, what I'm going to call, deeply quantum algorithms. Again, Shaw's you kind of alluded to when it came to, breaking RSA. So, this is an algorithm where we know that it can factor, numbers into their prime factors in, polynomial rather than exponential time. That is something where, there is a use case that we know where there is that killer app, but we don't have this for every single problem. If anything, we only have kind of two of those. We have Shaw's and we have Grover's, and they were both discovered just shy of 30 years ago. There's been a lot more work on these NISQ algorithms, on these variational ones, on these kind of, the sort of stuff Nick does, but it's still that open question of to what extent they're fundamentally quantum, or to what extent it's just that quantum gives us the language to be able to think and describe and discover them, but actually we can do a lot of what they do classically. So again, I just worry about promising that quantum will solve everything in an inherently quantum way.
But maybe I can jump in, and I would really want to learn from John about Internet of Things, and specifically the challenges that you have, because quantum is a solution for some problems, but I think it will help to understand which kind of problems can we solve with quantum devices if we put them on edge.
Yeah, I mean, so dynamic image analysis, cryptography, things put in the field which are far from the cloud, that require huge amounts of computational resource. I suppose those would be the three that I would reach for immediately. And as you say, those class of problems that we haven't thought about how to solve yet, that just don't, we don't have solution. We wouldn't think they could be solved computationally.
So there is one application that was not mentioned yet, which is quantum sensing, specifically working with quantum data. So in quantum machine learning, what we have discovered that when you work with quantum data, so states that come from measurement apparatus and process on a quantum device, you could do it exponentially better than if you just collect information and post-process it on a cloud. So in principle, this is something that fits really well edge applications. You have a correlated sensing network around you. You collect this information, you process it with some maybe special purpose quantum devices, and then you get superior precision. I don't know, maybe you can track the position better or do the predictions of, for instance, pressure. So there are many different options.
Okay, so I've used lots of different sensors in IoT in my professional career. I've not used a quantum sensor. Could you sort of expand on what that is?
For instance, it could be a magnetometer. So imagine that you have a detector of tiny magnetic field based on the defect in, let's say, nitrogen vacancy in silicon. And you can have a quantum device that will pick up small magnetic fields in a correlated way. So there will be different defects connected to each other, and it will have precisions orders of magnitude better than a classical device. So that could be one possible edge application that does not require cryogenics in principle.
Okay, and is this something that could operate at room temperature? Or at least sort of on a production line or in a sort of factory setting, or are we talking a particularly specialized environment?
So this is something that can operate at room temperature. It really depends on applications, but these sensors are being developed as standalone solutions. So at recent quantum technology showcase had a special stand that you could actually take those sensors buy and deploy. So they're not yet networked, and the processing quantum computing is not a part of that solution, but it's a sensor that you could really place and get improved precision just from the sensing itself.
Okay, so I'm going to ask a naive question. So yeah, we had CPUs first, then GPUs, and now we're seeing tensor processing units and neural processing units. Are we going to see quantum processing units come out? Is that a thing, or have I misunderstood how this fits in with the computational environment?
So we definitely see them already. QPUs do exist as cloud solutions in special environment. Whether we can move it closer to the edge, that's a question that for the future development.
Yeah. And again, I mean, comparing it as you did to GPUs and things, these are going to be tools for specialist kind of applications. It's not the case that a QPU is going to replace our CPU, for instance. It's the this will be a device that will help us with a special class of problems, and so being able to access it, again, if we discover more ways to use that for more local relevant problems, I don't want to be like that CEO of IBM who said, there will be 6 computers in the world. I don't want to be there will only be 6 quantum computers in the world. But equally, it feels like this current solution for quantum computing of cloud-based, having that sort of, accessible when you need it, but also not having it, in every home, is probably going to be the solution for a while, I think. Whereas, there are plenty of other edge applications for quantum, again, like Sasha was saying, quantum sensing and the like, that I think will be deployed and will be part of, again, people's, devices or on the edge far, far sooner.
Yep. And I would say the thing that's getting it one step closer to the edge is now co-locating quantum processors within supercomputing facilities. And that's not yet, completely having it in your home, but people are thinking seriously about, you don't actually want to have all the latency that comes from your supercomputing center calling some remote QPU that's in a lab. You actually want it. And, people have really been working on this. The Jülich Supercomputing Center in Germany is a concrete example of this. They have programs where they've started to co-locate some quantum processors. That's still quite a step away from having it in your living room, but this is something people are thinking about, and the integration with classical computing is, in the same way it is for GPUs, for any of these others, is going to be crucial. And having the fast interconnects, really thinking about how you use these in a hybrid way, how you use your quantum algorithm that's good for, or quantum processor that's good for a handful of things, maybe in tandem with a bunch of other things that aren't. The other thing that's worth flagging up is, if a quantum computer is used for training, but not actually for the inference part of the algorithm, they can influence things on the edge before they're actually located at the edge. You can actually have, for example, a simple example, you could have a boosting algorithm where you train it on a quantum processor solving optimization. And then once you have those strong classifiers, you can use them somewhere that's nowhere near the quantum computer.
Okay, so I'm going to ask another naive question. So when they trained ChatGPT, it took $6 million and 6 weeks to do that. Are you saying that a QPU or some equivalent could do it in a fraction of the time?
Well, this is a fun thing that we're kind of looking to explore. Maybe not, in terms of, training LLMs, but in terms of being able to use the fact that quantum machine learning possibly could be useful for in building models from sparser data sets, which obviously, that's kind of the opposite of what you gave earlier when we're dealing with, massive data sets and things like that. That doesn't seem to be really where quantum machine learning will give us an advantage. But if we're dealing with really small ones, I mean, again, something we've been looking at recently is potentially, can quantum machine learning have benefits for modeling pediatric oncology, where thankfully we don't have a lot of data points because, not many kids get cancer, thankfully. But obviously, if you want to build a model using that sparse data set, using standard machine learning techniques, that's quite difficult. So again, and I can't say that, quantum machine learning is better for this or worse, because it's work in progress, but actually being able to take this originally very theoretical thing, and then use devices that are being, made by the National Quantum Computing Center and made accessible via the cloud to test out this, is a really cool place, and is, as Nick says, kind of coming closer to the edge, or at least, closer to real world live applications.
Okay, so I'm hearing that we wouldn't use it to create a chatbot or some kind of large language model, but it's more its aptitude is to sparse data sets. What makes it better for sparse data sets?
Well, go ahead.
So the features that quantum devices process are different from what deep neural networks pick up. You typically study the global structure of operators and states. So one advantage that you have, you can work directly with quantum data. And second advantage, you could track correlations that classical processing would miss, because quantum computers inherently work with high-dimensional space and correlations. So we've seen it for scientific data. We've seen it for data that already involves quantum mechanics. And I guess that would be the first application. It's a scientific discovery. So trying to not to build LLM for large language model, but rather large scientific model. And at certain point, it will take signals from sensors as well, and that will become our kind of variant of quantum IoT application.
Okay, so if I was looking for a class of problems that we could focus on in IoT, would we look for ones where quantum sensing would have some kind of quantum sensing, or some sparse data sets where we'd want to create some models? Are there any other cases where quantum provides an advantage?
So it's still a matter of exploration. One that was highlighted is solving differential equations, or in general linear algebra problems. So there you can also have an advantage in doing transformations with exponentially improved scaling as compared to standard linear algebra. But it will only happen when quantum devices reach much higher scale, because overheads are significant. And there are also several outstanding problems one needs to solve before you have this advantage. So I would say we got the vision for near to mid-term, where we can build scientific applications based on quantum devices, and we can do linear algebra acceleration, but in the future when we have the full-scale quantum computers. Yes, Koorosh.
Yeah, I would like to add another perspective to it as well. So one of the usage that we have is about this kind of exploration that we recently used is the explainability of machine learning or generative AI itself. So let me explain the basics first. So imagine you want to explain the behavior of a large language model. So you have a large language model like ChatGPT and any other huge, let's say, large language models. So you have the input lengths of 1 million tokens, and you want to explain which token has more influence on the outcome. So one of the easiest way that you could do for a commercial tool like that is that you turn off and turn on different tokens. So you remove one word to remove the other words, and you see what is happening in the outcome, what is happening in the response. And based on these kind of perturbations, you get the understanding of what we call it, the kind of the behavior, which word is focusing, which one is the LLM is ignoring, which words, and so on. So doing this one with traditional perturbation algorithm and classical algorithms is super difficult and time consuming. But imagine that you kind of replace it with a quantum machine learning or with a quantum, let's say, exploration algorithm. So instead of doing this classically, you could do the perturbations by the kind of quantum algorithms, and then find the best perturbation or best set that can trigger the algorithm or the LLM to provide the response that you want. So these kind of explorations could help us to build more explainable and trustworthy AI solutions. We do the same kind of, let's say, algorithm for AI safety evaluation as well, when we need a kind of, let's say, huge number of perturbations. So we could use it in that direction.
Right. So, I mean, we couldn't use it to train a large language model, but it can in some way reverse engineer large language model to make it more explainable and safe in its performance. Am I understanding that correctly?
Yeah. So in terms of explaining the behavior, at least token level explainability, we could use this exploration. We could use it as an exploration tool to have a better kind of, let's say, outcome.
Okay, quick question from the audience. When can we expect a pseudo quantum module like Microsoft's in a home PC or laptop? Thanks to Nick Young for that question.
So I think this depends what pseudo quantum means. An actual quantum one, it's going to be a long time. If you mean something that was inspired by the way a quantum computer works, but is entirely classical, you can go and buy a Fujitsu digital annealer, which basically just performs very efficient simulated annealing tomorrow. I think it's rack mounted. I don't think it would quite fit in your computer at home, but you could have it in your living room. I don't think they're particularly cheap, but and then there'll be other things in between. I'm not sure exactly which Microsoft, because Microsoft has done a few things, which Microsoft effort they're referring to. I don't know. Does anyone else on the panel have an idea about specifically what Microsoft's been up to?
Well, it may mean working in Windows or something like that.
Oh, okay. Yeah, well, I mean, quantum software is probably a different issue there, and yeah, getting it to interface with everything else is, of course, important. But I think it would be a while before something that's really fully quantum could be there. Things that are various levels of, using the ideas you could get right now, using, something that's more inspired by the ideas like a photonic chip or, an optical chip that still isn't fully quantum, maybe that's a bit off. The real thing, yeah, having that locally is gonna probably be a while.
So what was the quantum-inspired computational unit you mentioned? Sorry, I missed that.
It's called a digital annealer.
Digital annealer. Okay.
And I mean, it's a chip. I mean, actually, I don't know if they sell them. They could sell them. But they certainly sell access to them. But that is an entirely classical device that came about from people being interested in quantum devices solving it in a similar way. But there's the word pseudo there, which, okay, by some definitions, that's, pseudo. It's fully classical, but it is, inspired by some of this.
So I've just seen that Nick has specified he's talking about the Majorana 1, which is a single qubit. As much as it's all these Majorana modes and everything like that, it's a single qubit. You can simulate that quite easily on just your home computer. I mean, obviously, the number of qubits you have in your system, the scaling in RAM that it takes goes up exponentially. But I think for instance, like a 16 qubit system is kilobytes, if that, maybe megabytes. 48 qubit system is like terabytes. 60 qubits is like petabytes of RAM. So a single qubit you can quite easily do in Qiskit or Penny Lane or, one of many other quantum, again, calling it quantum simulation because quantum simulation also means simulating quantum systems using quantum computers, but simulation in the classical simulation of quantum systems, you can do quite easily.
I think it's a very good question. It just shows that quantum computers, of course, to bring advantage, they need to be physical at large scale. But another type of advantage is training and learning how quantum physics works, or making it quantum inspired, so classically simulable. And there are lots of amazing packages nowadays that simulate quantum devices. You can look online, but in general, many people would use Qiskit and the entire package from IBM that has subroutine solutions. You can play around with a simulator. You could understand how the noise can be added to a system, and you could later run it on a cloud, just connecting to IBM's devices. You have Penny Lane from companies like Xanadu, which has tutorials, and explanation how subroutines and different protocols work. So that's another great opportunity to learn. And Microsoft also had quantum katas, which is a very old way of doing exercises in quantum computing, like coming from karate training, I believe. And then you could simulate it on a classical device, no problem, but it gives you understanding how physics works and how you can build new algorithms.
Fascinating. So can we go around the panel and just take a quick overview of what use cases are currently addressed by quantum and what you've personally experienced and what's in the pipeline?
So which way are we going around?
Oh, I was waiting for you to jump forward energetically. Nick, please go forward first.
Okay, I suppose I have. So I think here it is worth differentiating where there are provable algorithms with provable advantages and where there are more heuristic algorithms. So Jonte's already mentioned the two sort of highlighted provable algorithms. Sasha mentioned another one, which is linear algebra. There are lots of things where there's no formal proof that you have an advantage, but there's ideas people think there might be. Optimization is one example there that people have thought of a lot. That happens to have a lot of connection to machine learning. That's also the area I'm an expert in. But that is one where there is no formal proof. There are reasons that people think there might be, and I would say they're good reasons. But there's no formal proof that you'll have an advantage from many of these, and it is worth making that distinction. It's also worth remembering that we're just now actually getting devices that we can experiment with that can do more than what we can simulate classically. And so it is worth remembering that there could be surprising applications that come out based on people actually being able to play with the thing that you wouldn't have thought of without being able to do some experimentation, because we've been, having quantum computing getting serious with it since maybe the 90s. Quantum computing has gone a long time without a quantum computer, and that shows up in the history a lot. There's a lot of emphasis on formal proofs because it was the only thing you could do. If you came in the 90s and said, look, I have this cool algorithm, it might work, but I have no way of arguing whether or not it will, rightfully no one would care. Now if you come with that, people go, well, yeah, maybe we can try that. So yeah, I guess Jonte is the next on my screen. So
I mean, again, as Nick said, like highlighting Shores and Grovers, I think, those are two things that are going to be really important. I think, honestly, again, to echo Nick, a lot of it, certainly on the computing side of things, is just that we don't know. I mean, there was a bit of discussion, I think Koorosh mentioned these post-quantum cryptography protocols that people have come up with because of, fear of Shores breaking RSA encryption, which is what we use on most devices. But again, most of those, it's not that we know that they are able to defend against all possible quantum algorithms. It's just that we know that there isn't a quantum algorithm at the moment that can break their security primitives. Again, for any of these post-quantum algorithms, someone could turn around tomorrow, or even just not have published yet, and have sitting on their desk an algorithm which could break these primitives. We're in that fun kind of discovery phase, I think. And again, there are things that are maybe nearer term. Again, obviously, sensing is something that is close to my heart because there's a lot of cool stuff you can do with it. And it tends to show quite nicely the weird quantuminess when you're doing it. The fact that interference and things is giving you these sorts of advantages. But in terms of, the computational advantage, a lot of it is just that there's still a lot to play for. Which, again, if you're looking for an immediate app now that you want to, use to give you some provable advantage, maybe isn't great. But if you just enjoy researching quantum, like I certainly do, and I feel like probably a lot of the panel do as well, it's a great time. It's kind of kids in the candy shop time.
Should I go next?
Please.
So I already mentioned about the kind of one applications that we could consider for explainability, for example. But one other ones that I wanted to discuss is that some of the kind of, let's say, meta-heuristic algorithms that are existing for optimization, there are some kind of, let's say, improvement, not exactly using quantum machine learning or quantum computing, but they were trying to mimic the quantum behavior. For example, they are saying quantum particle swarm optimization algorithm. So by mimicking the quantum behavior, they were showing that they could improve the divergence or convergence of some of these optimization algorithms. So there are kind of existing papers or research papers in this field that showing that mimicking the behavior of quantum computers could help us to kind of, let's say, have a better optimization, but it is not 100% proof kind of, let's say, approach. So they are doing research and trying to find which one is best and which one is not. So a lot of people are researching in this domain, as far as I see.
I mean, that's the quantum-inspired algorithms that Nick was talking about earlier, which, again, I think, Nick, you might have one of the big reviews in that area, right?
No, not really in quantum inspired, more in hybrid quantum classical.
Okay.
But yeah, I mean, there's a lot there. We'll let Sasha.
Yeah, I got the privilege to talk last in the cycle, and it's good that we still have gaps. We still have something to say. So together with optimization and cryptography, so all the protocols that basically do computation which is farther away from physics, or quantum inspired protocols, we have material science and chemistry. That's a big application. Quantum computers have provable advantage in finding properties of matter, and that's, if not near term, it's certainly coming up within next decade. We have drug discoveries that can be built on advantages of molecular simulations. We have speed up for differential equations, and there are proposals by companies like Google where their team calculated that fusion can be improved with quantum devices. So these are the big applications in the future. I would make a bold statement about near term. I believe that the generative modeling can benefit from quantum computers, because quantum devices are probabilistic. We sample probability distributions each time we do the measurement. So that's one application that I see coming, and the supremacy experiments by different teams, they're based on generating samples. So we just still don't understand how to treat them as relevant distributions, but that's something we are working now.
So does that, another naive question, does that lead to problems with believability and reproducibility like we have with large language models? As you say, it's probabilistically based. You might not get the same answer twice running.
Certainly, yes. And that's part of the discussion, that to show that you supremacy is a statement that you do something that's impossible to do classically. So you sample the probability distribution that's extremely wide, so you have probabilities across a very large number of possible outcomes, yet you need to prove that this works correctly. And without classical simulation is just impossible. So checking and understanding whether it works correctly or not is a challenge that's being addressed now. There are a few approaches by planting solutions in your probability distribution such that you understand that there is a hidden string inside, and later measuring on two or more devices just to check that it's reproducible. this is one approach that people take. But you're absolutely right, John, it's a probabilistic machine, so verifying that it works correctly is very important to call it computer in the future.
Fabulous, thank you. So moving on to our final agenda item, future cybersecurity at the edge. So I was sent an email shot from Elector magazine, which is sort of a hobbyist electronics magazine the other day, talking about quantum proof cryptographic algorithms. You need these because quantum is going to change everything, and because your IoT will be at the edge for a lot longer, you need to have a quantum proof cryptographic algorithm now. What do we think about cybersecurity at the edge?
I think it depends on what you're keeping secure, right? People think about this. Cybersecurity people a lot of times will think about, okay, well, what's the sort of shelf life of this data you need to keep? And if it's data on your fridge about your activities day to day, that probably, if someone saw that 10 years later, it probably doesn't matter. There's certain financial and government records that, someone finding it 3 decades later could be really damaging.
I think the perennial problem in the IT world is getting hacked. And if you've got like password hashes, hashing algorithms just become outdated and crackable over time. It's just so all of your suite of IoT devices, thousands of them, don't become a zombie botnet for some teenager in a garage somewhere.
Mm-hmm. And so I guess with a device, it's how long is the device going to be up? Is it going to still be functioning when quantum comes? And for some longer,
if it works, they won't change it.
Yeah. So the answer may start to be yes. The problem then becomes that a lot of the way we know factoring is hard is that we've thrown a lot at it. We don't really, if you look at the theoretical computer science behind it, as far as we know, factoring isn't an NP hard problem. Not a lot would change in theoretical computer science if factoring was easy. We know it's hard because we've thrown a lot at it and none of it's worked. Well, we don't know. We suspect it's hard because we've thrown a lot at it and none of it works. This is the problem with all the post-quantum stuff too. Unless you have another way of really showing it's secure, you kind of just have to put it out there and hope no one breaks it.
I mean, because again, in terms of, so for RSA, which is, the kind of key family of public key crypto protocols that we have, again, we know that is vulnerable to Shor's algorithm. And I think Craig Gigney said, who works at Google and is our kind of best calculator with all of these tips and tricks, how many qubits we need to do Shor's algorithm to break RSA 256, I think, which is the current one that tends to be used. I think his most recent estimate, if I'm right, was about 1 million qubits, which again is coming quickly. There has been a little bit of a quantum Moore's law going on in terms of the number of qubits on viable quantum systems. So again, moving away from using RSA is going to be more and more important. As Nick said, moving to these quantum proof or quantum secure or post-quantum cryptographic protocols, we have no guarantee they're really quantum proof. We just know that there isn't a quantum algorithm at the moment that can break them. As you say, that doesn't mean some kid in a garage couldn't figure out an algorithm which could.
Or a classical algorithm that can break them.
Exactly.
That's the other problem. People haven't tried classical algorithms on these. This has happened before.
Yeah.
I don't have the references to hand. I believe there was one that literally a teenager figured out how to break, classically. Like they actually broke some post-quantum crypto system just because the people hadn't thought of something who designed it. I don't have the reference to hand, though, but I believe...
Was it NIST who was doing their test of these post-quantum encryption algorithms to try to establish.
It may have been.
Yeah. And where again, as you say, some tricks that are not actually quantum, which discovered to break some of these.
Yep. Now, a trick there you could use is you could do RSA, and then you could do the post-quantum on top of that, or the other way around.
Yeah.
So then you have to be able to break both, which maybe you can, but
yeah. But again, I mean, there are quantum solutions as well. As I say, using quantum key distribution, which effectively sending not the information, but sending key and then building the encryption for the information based on that on quantum particles. So it's not just that, it's mathematical tricks for this is a difficult problem. It's that through the laws of physics, through the fact that in quantum mechanics measuring something changes it, means we can guarantee the security of these things, assuming our hardware is exactly as it is in these idealized proofs and things like that. Is going to be a way forward. And again, I know it's what China is currently doing. They've massively invested in their infrastructure. You've got big quantum fiber cables going all the way up the East Coast. You've got what's the satellite set that Jian Wei-Pan put into space to do space QKD. There's been big investment in doing quantum key distribution that we've kind of lagged a bit behind here in the UK. I mean, we've got the it used to be the Quantum Communications Hub. Now its successor is the Quantum Networks Hub, which has a project within it, which is to, again, have, photons carrying key going from satellite to base station rather than the other way around. But again, we're still at the stage where, it's the base station is being driven around in a little mini, hatchback thing by a PhD student. There needs to be more investment in defending against these things, but equally assuming that because someone is selling you something they're claiming is quantum proof or quantum safe, assuming that is quantum proof or quantum safe is always going to be a bit risky. Oh, yeah, exactly. And again, Nick said in the chat, keeping a human in the loop. Yes, but also humans tend to be one of the most vulnerable parts of any security thing,
Social engineering.
Exactly.
Yeah. Okay, so we have 5 minutes left. Can we do quickly for our panel? Where do you see quantum being in 5 years' time, either at the edge or otherwise? Where are we going to be? Koorosh, where can you go first, please?
Yeah, one thing that I wanted to add on top of all those discussion that we had is that with regards to kind of quantum machine learning and quantum computing, if we assume that they can be used for things that we have as a machine learning algorithm, like classical ones, although I feel that they should be used in different directions, not similar to what we have at the moment. But if we imagine that we could use them as a kind of competitor to the current AI solutions or generative solutions, still the problems that we have for example, AI safety or AI explainability exist. So in a traditional or classical AI algorithm or classification algorithm, you have the idea or problem of out of distribution detection or out of distribution causing or lowering the performance. So the same could happen for the quantum machine learning classifiers. So someone can easily go to Qiskit and try one of those existing classifiers, quantum classifiers, and see how out of distribution can cause or reduce the performance of these models. And also we have different circuits in design for example, a quantum classifier. So we could have the idea of explainability showing that, okay, which circuit was more influential for the decision and so on. So these are the things that I think should be considered as a trustworthy layer on top of any quantum machine learning or quantum AI solution.
Thanks for that, Koorosh. Who's next?
I can go.
Cool.
Very simple. In 5 years, I believe that we will have a quantum advantage. We can already see the signs of it. So solving problems that are just impossible to do classically with meaningful amount of resources. We will be accessing quantum cloud devices, not the edge, but cloud devices, to solve scientific problems and understand which new algorithms we can build. And I believe in 5 years, we will actually discover new protocols that were unknown in 90s, because we can program real devices and not just do theory. So exciting time, and we'll see where we get.
Great. Jonte?
Again, I think pretty much echoing Sasha's vision there, that I think in 5 years, we'll be close to being able to have a quantum system that can deploy Shor's algorithm, if not there. I think in other areas, we'll have some sort of quantum advantage. Again, I know Google have been hinting around some of these out-of-time order correlators and things and their ability to calculate those. So there's things where it looks like we're getting close to quantum advantage. I think in terms of practically, I would like to think that we would have more infrastructure ready and set up for quantum key distribution, quantum secure communication. Ideally, proper infrastructure for that going up and down the country. I'd like to think similarly, quantum sensing, quantum imaging solutions, hopefully again tied potentially to quantum machine learning or variational quantum algorithms for things like, drug detection, drug discovery, for instance, or, quantum chemistry in that respect, and medical imaging, medical classification, actually being able to start using some of these things for healthcare.
Great. And finally, Nick.
So I think there will be some new applications out there. I tend to agree with that. I think we'll be well on our way toward, some of these fault tolerant algorithms. I don't know if we'll quite be there in 5 years. I'm maybe a little more pessimistic on that, but that it's hard to know. A lot of this depends on the hardware development. I do think there'll be progressively more desire to put these devices, integrate them in places. I don't think they'll yet be in your home or at the edge yet. I do think, however, that a good number of, if not most, sort of HPC, high performance type research centers will have some kind of QPU integrated in. So, that step from the cloud, I think will start to happen. The integration with the large scale classical technology, rather than now where you mostly have a standalone cloud offering that anything that has to go to it from another quantum or classical processor has to go through the internet first. That's really slow. If it just goes through some cable or fiber or something from the room next door, that's much faster and not having to go through all these protocols and not risking being hacked and all of this. And I think, I think the other thing to keep your eye on for quantum machine learning is a lot of the developments people have made in tensor networks. So these are methods to try to simulate quantum devices. And, they're basically, someone comes up with a claim that their device can do something you can't. Someone says, well, the classical algorithms aren't very good, let's make them better. They develop typically a tensor network algorithm to try to compete with that. And there's sort of a space race there. And I think people figuring out how to use those in machine learning is also going to give some real returns. And those are completely classical, but they're simulating quantum systems.
Fabulous. Just remains for me to say that we're back in January. Thanks for the audience for submitting their questions. In January, we've got a talk on responsible AI at the edge. And in February, we've got a talk on game changers in wearable technology. I'd like to apologize once again for the technical problems we had at the beginning. Sorry about that. Thanks so much to our panel, Sasha, Koorosh, Nick, and Jonte. Your knowledge has been amazing, and thanks for enlightening us all.
Thank you.
Thank you very much, John.
Thanks,
everyone.
Thank you.
Bye-bye, everyone.
Thank you. Bye.